Hey Chem friends, my name is Jeremy.
And my name is Ari.
This is our presentation on what lambda max is in terms of emission spectroscopy and what determines it.
In terms of emission spectroscopy, lambda max is a wavelength emitted most by the substance within a region of the emission spectrum, also known as a peak, which corresponds to the wavelength with the highest intensity in said region. Macroscopically, this translates to being the color observed by the eye, because intensity is the amount of photons of a certain wavelength the substance emits. Therefore, the substance is emitting the highest amount of photons of the wavelength lambda max, and therefore the eye registers more of those photons, and the brain interprets the substance as being that color.
Quantization is a principle that states that electrons can only absorb discrete amounts of energy. Changes in electronic state is not gradual like an escalator. In order to increase in energy levels, a set amount of energy is needed to induce this change, like a stair-step. The electronic structure of a molecule encompasses the shells in which electrons may be found, including the inner and valence shell, and how they are oriented with respect to one another in terms of the energy gaps between them. Molecules with more protons typically have more electrons if they are neutral. However, the increased attractive pull or attractive force, the result of having more protons, brings the energy levels of the molecule closer together, reducing the potential energy gap between them, thus emitting a photon of lower energy. For example, helium and hydrogen have the same valence shell, but because helium has one more proton, the lowest energy per photon it emits will be of a greater wavelength than that of hydrogen, 667 nanometers versus 656 nanometers.
The principle of quantization and energy release can be compared to the stages of drunkenness a college student may experience. As the graph shows, at designated blood alcohol concentrations, certain symptoms follow. This is analogous with the different energy levels within an atom. Alcohol is the energy in this case. As the student consumes more alcohol, their energy will increase. Certain alcohols will induce certain stages. For example, some students may not be fazed by beer, as their body can regulate this intake of lower concentration of alcohol without producing an increase in drunkenness. But vodka, on the other hand, will yield a certain level of intoxication. In order to return to its ground state, this energy needs to be released. In an atom, a photon is released at a certain wavelength. For the college student, they may throw up. Just like the levels of alcohol a person can tolerate is determined by the characteristics of the person, quantization levels are determined by the characteristics of molecules, specifically how many protons and electrons that molecule has, as well as the molecular composition of said molecule. Because all these factors contribute to the electronic state of the molecule, which will directly influence emission events because the electronic structure will determine the gap in potential and kinetic energy between the ground and excited states. This quantization energy is a differentiating characteristic.
When mixing two substances that emit only one color, it is highly likely that the emission spectrum will have two local lambda maxes, one for each peak. Specifically in this lab, the emission spectrum showed local lambda maxes at 2 points, one the green range at 506 nanometers and one the orange range at 617 nanometers. When our eyes absorb photons from both of these peaks at once, our brain interprets this as an orangey coral color. More orange is observed than green because this lambda max is a higher intensity, meaning photons of 617 nanometers were emitted more.